Good evening, everyone. Thank you for joining us for the UW Data Science Seminar. I would like to introduce our guest today, Dr. Emma Perkovic. She's an assistant professor in the Department of Statistics at University of Washington. Before coming to UW, Emma completed master's and PhD degrees at ETH in Zurich and a bachelor degree in mathematics at the University of Belgrade. Her research interests are focused on causal inference from the perspective of graphical models. I'm happy to have Emma here today, and she'll be sharing with us more details on identifying and estimating causal effects with incomplete causal information. Please welcome Emma.
Thank you. Thanks, Nicoletta. Thank you for having me. All right. Woo. There we go. It works. Okay. So for the talk today, I thought I'd give kind of an overview over my work, what I'm interested in, and some results that came out of that. The talk is very high level, so I hope you're able to follow most of it. I'm not going into proof details. I'm leaving that off for papers, so so the talk is called Identifying and Estimating Causal Effects with Incomplete Causal Information. And part of this, so a lot of this is joint work with Richard Guo, who is soon to join the UW Biostats department as a faculty member. And then there's work with some other people. Andrea is also at Biostats, UW Biostats. Okay. Right, so I'm going to introduce this example of Stanford marshmallow experiments, because I think a lot of people are familiar with this concept. So this was an experiment that was originally run in the 1970s, led by Walter Mischel, who is a psychologist, and was a test on the ability to delay gratification. So children, roughly in total, about 100 children that were about 4 to 5 years old, were essentially tested by being put in this room and being given the option of either having like one little reward now or waiting 15 minutes to have 2 rewards. So the reward that they used was either a marshmallow or a little pretzel, but the name marshmallow test kind of stuck in the end. And so what they did was they left the child in the room with like a single marshmallow, and after about 15 minutes, the scientists came back into the room and they saw whether the child has eaten the marshmallow or not, and if not, they got another marshmallow. So the children were also timed how long it took them to eat the marshmallow, and that was kind of a measure of the ability of this child to delay gratification. Now, what is really interesting about this experiment is not really the initial setup necessarily, but the fact that this cohort of children from the original experiment was followed over the course of their pretty much entire life up to today. And many follow-up studies kind of try to compare the groups that were able to delay gratification longer and groups that weren't able to delay gratification, and saw whether there were some differences, some major differences between groups. And so what they noticed in these follow-up studies is that the children who were able to delay gratification longer generally tended to have better academic scores, better various health outcomes, and so on. And so they kind of noticed, there seems to be a connection between this ability to delay gratification and, let's say, later academic success. So, of course, the study was super, super influential, and there were many articles kind of following up these results, saying how having self-control as a kid can affect your health later, so implying essentially that there is some causal effect from this ability to delay gratification as a child into later adulthood, maybe academic success, maybe health outcomes, and so on. So, so I'm interested in questions of this form in the sense, so suppose that we can perform some type of causal intervention. So let's say we can perform some intervention. Should we perform this intervention, right? So if this indeed is an ability that helps you succeed later in life, should we kind of impose this, have a little class that the kids can take, for instance, on how you delay gratification and things of that nature, right? So is this delay of gratification actually responsible for this later in life success? And so I'm going to be making some assumptions in this talk. So I'll go through those in a brief moment. I just wanted to say before I get into this that there were many follow-up studies for this case, and various parts of it were debunked later on. And so this is the story of, I think, the marshmallow experiment is kind of the story of assumptions. So what kind of graphical or causal models you assume, and what can you conclude from these models, and like the limits of what we can do from observational data versus experimental data. So in this talk, I'm going to be assuming a few things. So first, I'm going to be assuming I have access to some observational data and some maybe domain knowledge on childhood psychology or something of that sort. And when I say observational data, I mean that I just observe the child's ability, let's say, to delay gratification and later academic success. I do not at any point kind of intervene and incentivize the child to take certain classes or anything of that sort, right? So we're just observing, we're not intervening. And so you might ask yourself a few more questions after knowing this first part. So what else do we need to know to actually be able to estimate various causal effects? So one thing that you might ask yourself is, well, do we know all variables that could explain or moderate this link that we are kind of tenuously scribbling on here? And do we know all the relationships between these variables, right? So you may assume yes or no to both of these, and so I'll be part of this talk. So now we're going to go to a slightly more complex system. So I'm sorry, it looks kind of washed out, but I hope you can all read it. So we have on the left-hand side this delay of gratification, on the right-hand side this later academic success, and now I'm including some variables that might relate to one or both of these variables. So one criticism of the original marshmallow experiment was that it didn't take into account the socioeconomic status of the children that were participating in the experiment. So one criticism was like, if you control for the socioeconomic status of the parent, that this causal effect might go away. So this effect of the delay of gratification on, let's say, later academic success. They also posited various follow-up results that maybe this effect might be mediated through some other important qualities you encounter later in life. So perhaps your ability to complete words or ability to memorize sentences. And maybe there's some other variables that relate to some of these, but not all of these variables. So for the rest of the talk, I'm actually going to be assuming that this is one kind of causal explanatory graph for how these things relate to each other. And so the socioeconomic status here is kind of a giant variable that can include many things. So I'm not going to go deeply into that. Right, and so we have this delay of gratification, later academic success, and then these variables that relate to this system. And this type of graph here is known as a directed acyclic graph. So it's directed because all edges are directed. It's acyclic because there's no loops back into a starting point. And it's causal because of how we are interpreting these edges, right? We're interpreting these edges to mean if I intervene, if I kind of input something on the delay of gratification, that should affect these downstream variables. So the nodes are variables in these graphs. Okay, so let's get a little bit more deeply into what I mean by intervention. So in a classical experiment, what it means when you intervene is that you randomly assign a certain treatment or control or something third, right? So in this randomized experiment, we're able to kind of fully control this treatment variable, in our case here, this delay of gratification, and so we can set it to take a particular value. Or that's the assumption in an idealized world. So graphically, how you can represent that is by kind of cutting off all other inputs into this delay of gratification, right? So now because I'm assigning this in any experiment, there's no more inputs from some other variables. And so this is the kind of graphical representation of the system under this intervention. And so when we perform experiments and we want to measure causal effects, you can see that, right, in this type of intervene scenario, this any kind of change in the delay of gratification can propagate through this graph into later academic success only through causal paths. All right, so in this scenario where you intervene, you can kind of just compare, for instance, the means of the outcomes in different treatment groups, and that should give you something that you can interpret causally. Right, so you can kind of reason about this interventional distribution of the response. So for me, Y is always the response and A is the treatment, and that can give you a causal effect. Now, we don't have data from this scenario. We have data from this scenario where we are not randomly assigning the delay of gratification. We have some inputs that might act on both our treatment and our response, right? So these are known as confounding variables. And so we measure data from system like this, and we may be able to reconstruct something about the observational probability distribution of these random variables. So I call this observational distribution or observational data. So you may have access to various functions of this observational distribution, but the issues with using this to estimate causal effects is that in general, this interventional distribution that you would like to reason about, we had on the previous slide, is somehow different from this observational distribution. And we need to kind of account for these differences if we really want to use some observational functionals to reason about the interventional distribution. So it's one first problem that you may have. And then the second problem is that we may not know this full graph, right? So I'll get to that next. All right, cool. So I'll just replace everything with A, B, C, D, E, Y because it's easier to write. And this is the same graph that we had in the beginning, and this, I'm assuming, is my causal DAG, right? So in this graph, I'm assuming there is, just one second, a causal relationship between A and Y. Yes?
How is the error from the A not causing it to this database cycle?
Okay. So if you had, yes, thank you. Oh, yeah, repeating the question. So if I understood correctly, this is about what do I mean by a cycle, essentially here? So I mean a directed cycle. So this ABC and AC do not form a directed cycle. So if this C was pointing to A, so if I had an arrow from C to A, then it would be a directed cycle. So this is what I'm assuming away. All right, thank you for the question. Okay, great. So this will be our causal directed acyclic graph, or a causal DAG, throughout the talk. And so, okay, I skipped ahead a little. So in general, if you have data from the observational setup where these are all the random variables involved in this causal system, what you can infer from this data, let's say by learning various constraints that are present in the distribution, such as conditional independencies or something of that nature, is you can learn a structure such as this one. So from observational data, without assuming more about various parametric forms or some other domain knowledge that might be present here, we can at most learn a structure like this if this is our true causal DAG. And so let me just take a moment to explain. So this has a very annoying name. It's called a completed partially directed acyclic graph. So it has both directed and undirected edges, right? And the directed edges match what we had in our original DAG. And what the undirected edges mean here is that, well, we know that there is a causal relationship between A and B, for instance, but we don't know whether A causes B or B causes A, right? So in this, what is represented by this kind of partially directed acyclic graph, this is kind of a summary graph representing an equivalence class of DAGs that could be true, but we don't know which of those is actually our true causal model, right? From observational data, we can only learn this type of structure unless we want to assume something more about parametric forms or something else. So for instance, what could you assume that you know more? So perhaps from previous experiments or a knowledge of psychology or something like that, or society, you may know that, well, I know that if there is this causal edge, if there is an edge between E and A, that it must be E that causes A and not the other way around. And so you might have this knowledge from experts or previous experiments or some model restrictions that you're willing to assume. And then you can use that knowledge and further propagate it to conclude some more information about this model. I'm not going to go into how we do that, but just note that with observational data, or these constraints in observational data, and this extra knowledge that you're willing to assume, you can learn this structure, which is known as a maximally oriented partially directed acyclic graph, horrible name, MPDAG for short. You can think about this graph as kind of an in-between between our DAG, which is fully informative in terms of these causal orientations, and the CPDAG, which is not super informative, right? So this will again represent an equivalence class of DAGs that are possible, but will generally be a restriction of the original equivalence class that you started with. Yes? Yeah, good question. So the question was, do the gray arrows come from domain knowledge? They come from, so these gray arrows come from just some conditional independence constraints that would be present in this model. And so they are something we can conclude from that, if we're willing to assume that these probabilistic graphical models can be interpreted in this particular way. But no, they should just come from conditional independence constraints. Yeah, thank you. Okay. So the questions that I'm interested in working on, among others, are if this is a type of structure, let's say that we can reasonably learn from observational data or from observational data and domain knowledge, when can we reason about causal effects given structures like this, right? So that where you have some incomplete causal information in terms of some edge orientations or something of that sort. All right. Long intro. All right, so I just wanted to walk you through kind of how I think about these problems. So when I think about a causal question, this is what kind of goes on in my head. It's like, oh, okay, I have a causal question. What I will do is I will gather some data and some domain knowledge, and I will use this information to learn a causal graph. So I'll speak briefly about what I mean by this. And then I want to use this learned causal graph to identify a causal effect. I'll talk about that later. And if that is possible, great, I will output an estimate, and that will be my causal answer. And if that is not possible, then I want to do something else. So I'll talk about these two things also later. All right, so what we are assuming here in this talk is I will be assuming that I have access to observational data and domain knowledge. I will be assuming that I do know all the variables in the causal system, so I can briefly talk later what happens if this is not satisfied. And I will not assume that I know necessarily the relationship between all the variables. So I will allow some of my edges to be undirected. That's what I mean by this third point. Okay? And so after this, I'll have two questions. So can we uniquely identify the causal effect or a set of possible effects, if not a unique set, a unique effect? And two, how can I measure how strong this relationship is? So how can I construct an estimator that has some good properties? And so just briefly, what I'm kind of leaving out here is that throughout the talk, I will also, just one moment, I will also assume that I have access to this learned causal graph. And so what I mean by a learned causal graph is either something that you've hypothesized with your expert, or something that you've learned from data using, a causal discovery algorithm, or something in between. So it could be something that you've posited with the expert, and then you've said, well, I am not sure about these edges, I'm going to leave those undirected. So you kind of moved away from something certain to something more uncertain. Yes, there was a question, yes. Oh, this one? Yes, I can explain on that. So I'm assuming that in this system of variables I'm measuring is everything that could interact with my treatment and my response. So I'm assuming I'm observing all confounding variables, which is not necessarily something that is super realistic in a lot of scenarios. So there's versions of various things I'm going to talk about today for that setting. Of course, we can conclude much less in that setting. But for kind of simplicity, I'm just discussing this basic scenario where I'm assuming I observe everything. So there's no hidden confounding in this case. Yes?
Is the constraint that it has to be acyclic, like assumption in, like, could there be, cycles that you have to ignore in order to do that?
Yeah, that's a great question. Yes, this is a fairly restrictive assumption, and it's not one that we can check. So it's something you assume and then you have to live with. I will say it's a very common assumption in causal inference. However, it's definitely not necessarily realistic in many scenarios. So there's ways to deal with cyclic systems, but they generally require using various stochastic differential equations, and so I'm not doing that here. So you need to get system to equilibria, and various conditions need to be posed on that. So this is not part of this talk, but there's research in that area too. But thanks for the question. That's a very good question. All right. Cool. So I've mostly worked on the second part, which is that I assume I know a causal graph from somewhere, and then I want to use that to identify a causal effect, or if not, do something else. And I've color-coded these papers here just to show you what they match up with, though I will kind of speed through the slide. So today's talk is going to be talking about some results from these three papers. All right. Long setup. Okay. So how do we connect these graphs with distributions? So for those of you who may not have taken classes on probabilistic graphical modeling, this is just a brief intro. So I'm going to assume there's some observational distribution, fx indexed v, and then there's some interventional distribution, let's say fx of v, when I intervene and set xa to some fixed value. And I will say that a DAG is causal if this observational distribution can factorize according to the graph. So each variable given its parents in the graph, and the product of those conditionals gives you the joint density. And also I require that all the interventional distributions also factorize according to this DAG. And in fact, here you can see that I'm going from something interventional to something observational, right? So these parts on the right are the same here, except I'm dropping the term on A. So looking at this example, this joint distribution of A, B, Y factorizes Y given B and A given B, so A parent is B, and B, and the interventional distribution when you intervene and set xa to some fixed value, little xa, factorizes as just these two terms. So notice that I just dropped this term here. And so for people who are familiar with probabilistic graphical model, this first part is quite clear. So if you have a DAG and a distribution that factorizes in this way, it's called a Bayesian network. If you have both of these things, it's called a causal Bayesian network. So that's how we connect graphs and distributions. So how do we reason about total effect? So total effect or a causal effect, I will label it tau AY, is going to be some function of the interventional distribution of the response. So often in experiments, this is like a contrast of means between treatment and control. So that's what I'm writing here, for instance. But it could be any other function of the interventional distribution. So it could be an odds ratio, risk ratio. It depends on your question of interest. So for me, I will say that the total causal effect is identifiable if this interventional distribution can be expressed as a function of this observational distribution. So for me, identifiability means I can actually compute this in some way or estimate it from observational data only. And so now, if you remember the previous slide, and you've thought about this before, if I know what my causal DAG is, then by this definition, every total causal effect is identifiable. And this is because this interventional distribution here is just a marginal of a joint interventional distribution. And on the previous slide, we've seen that this can factorize in terms of these observational quantities. So, right, so this interventional distribution is identified using this type of formula. This particular formula is often referred to as the G formula of Robbins or Pearl. All right? Great. Now, so that's the case when you know the causal DAG. However, I'm in the setting where I do not assume I know the causal DAG, and in that setting, this is not always possible. So here I list a bunch of results that tell you something about identifiability in these general graph classes. And so I'll talk more about it later. But just so you know that there's a vast literature on this, and I've contributed some to it, but there's a lot of work still ongoing here. Okay, so let's think a little bit more about this. So when I say that I can identify a causal effect in a structure like this, I mean I can express it in terms of observational quantities. And for any DAG in my equivalence class, if I was to estimate this, I would get the same result, essentially. That's how you can think about this, right? So let's say I have this graph, which if you remember from previous slides, this is the graph that we could hypothetically learn from observational data in that scenario. So just observational data. And so here we are interested in the causal effect of A on Y. And we're wondering if this knowledge here is enough to let us identify this effect. And so in this case, the answer to that is no, actually. sorry, I ran across. So in this case, if this is all we know, if we don't make any other assumptions, we cannot uniquely identify a causal effect here. And so the reason for that is because, well, this condition here, which is necessary, is not satisfied. But a more intuitive reason is that we have here a path, let's say this path A, B, C, Y. This is known as a possibly causal path because you have these undirected edges and then a directed edge out of C. And there are DAGs in the equivalence class where this path is causal, and there's also DAGs in the equivalence class where this path is non-causal, right? So you can think about this as, for this amount of information that kind of propagates, or for this association of A and Y through this path, we don't know whether we should count it towards the causal effect or kind of remove it, in a sense, from the causal effect in the end. Right, so this necessary condition for identifiability here is that we want all of these possibly causal paths to start with a directed edge out of our treatment, A. So here we cannot uniquely identify a causal effect. However, in this particular setting, we can identify, instead of a unique effect, a set of possible causal effects. So we can get a range. Yes? Yeah. Yeah. So this is a summary graph where this undirected edge means that in this equivalence class of DAGs that this represents, so in this equivalence class of DAGs represented by the structure, all of the DAGs will have the same skeleton, so they will have the same kind of edges present, just with different orientations. So in particular, all of the DAGs in the equivalence class will have these directions from E to Y and C to Y. But for instance, for this edge A to B, there will be at least one DAG that will contain edge A to B and at least one DAG with edge B to A. So it's not as simple as kind of listing out all possible combinations of edge orientations for the undirected edges, because you need to be careful of cycles and some other things that I won't get into, but you can think about it in that sense. Like, let's say I brute force list all the options for all combination of these edges, and then I'll just remove some that are like cyclic or something else. Yes?
In like a practical analysis,
Yeah.
do you do that? Do you like generate all possible classes and then like try to estimate it from those versions of it?
Oh, it is a great question. So, yes. Well, sorry, and I forgot to repeat the questions. So the question was, is that what we do in practice to get at this range of possible effects? That's totally one thing you can do. So in this slide, that's the first thing you can think of, right? So great question. The answer to that is yes, because I know that given a causal DAG, every total effect is identifiable. What you could do is just run through your entire equivalence class and, like, in each DAG, estimate this causal effect, and then you output this set of possible effects as your result. I'm not sure if that was your question, or if your question was, like, do we just brute force through all the combinations?
I was more like, do we use all of the like possible acyclic DAGs?
Do we need all of the possible DAGs to get at this estimate?
Yeah.
No. Okay. So I will, so hopefully that will be explained in the rest of the talk. All right. So now the goal has changed. We can no longer identify this causal effect. And so instead, what we want to focus on is the set of possible total effects. So we are interested, instead of point identification, we want the set identification. And so if you like thinking about equivalence classes, you can think about like partitioning this equivalence class into parts such that in each partition, the effect is identifiable, and between the partitions, the effect is different in a sense, right? So complete here, I mean that this partition, so the effect is identifiable under each partition of the equivalence class, and minimal in that the effect should be different between different partitions. Okay, so you can think about like slicing a pie. Yeah, okay, great. Okay, so for the completeness, that's pretty easy to achieve in the sense that I know that if I know the DAG, I know all the effects. So you could just enumerate, so you could do the partition that is essentially each So you can partition so that each partition contains one single DAG. And so then you have all possible DAGs, and so you can estimate the causal effect in each. But there's more clever things that you could do. So for instance, people had noticed since 2009 that what's enough to be able to estimate the causal effect, or actually people have known this for longer than that, but never mind, is if you just know the neighborhood of your treatment, if you know what goes in and what goes out, you can kind of know what you should control for versus what you don't need to control for, right? So you can, instead of enumerating over the entire equivalence class, what you can enumerate over is just the neighborhood of your treatment, all valid configurations for the neighborhood of your treatment. So that's already enough. And then more recently, Liu et al. Also proposed, actually what's enough is just to look at the orientations of those edges next to your treatment that are undirected, that are on these possibly causal paths to I, right? And that actually seems to match up with this criterion that I said is necessary. So we need to know the edge orientations of all of these edges on possibly causal paths from A to I, right? The first edge, the one that's next to A. And so, as you can imagine, the first part here, so enumerating over all DAGs, this is not minimal. So clearly there will be DAGs with duplicates. So there might be DAGs that have just the same effect, and so you're enumerating too much. Neither is the second option, so the valid parent set, that's also going to not be minimal, so you might have duplicates again. Surprisingly to us, the third part is also not minimal, which is surprising because it seems to match up exactly to what is the necessary condition for identification, so why would it not be minimal? And so just a little detour on why should you care about minimality at all. All right. One reason for that is that what we're trying to do here is we're enumerating over all possibilities, right? And then in each of these partitions or graphs or whatever, we want to estimate the causal effect. Now, you may, because of the structure of the graph, end up using a slightly different estimator because it's slightly different estimator is proposed by this graph. But they might have the same effect in both graphs. And so in your estimation procedure, you may just get different numbers for the estimates just because you're using different estimators, not because the effect is truly different, right? So you may be estimating duplicates, and then in your estimate, because you don't have infinite samples, they look different when they're not actually different. So this project was about kind of distinguishing this, what are things that are causally different from things that would be like statistically different or numerically different because of like smaller samples or something of that sort. Okay, so I think in the end I'll only have time for this first project, but that's fine. So let me walk you through what we did here. So how can you think about enumeration here? And let's see what Liu et al.'s proposal would do here to get you the enumeration of all possible effects. So what we want is we want all the edges on these, so the first edge on the possibly causal path to be oriented. And so you can, in your graph where not everything is oriented, you can just pick one of these edges that you still need to consider, and then you can kind of create two realities. One in which you imagine that someone has given you domain knowledge that this edge goes in one direction, and the other in which you imagine that actually you know that this edge goes in the other direction, right? So you create kind of this tree. And so you can then keep recursively operating on these graphs, right? So if there is still some edges that need to be oriented, you can further kind of recursively partition these equivalence classes until this effect is identified in each partition. Okay, and that's essentially what Liu et al. Proposal would be doing. So let's see, given our graph, what that gives us and why it's not minimal. And so here is a simplified version of the graph from the beginning. So I removed D and Y just for simplicity. It's fine to leave them in. It just makes this enumeration not fit on my slide, so I've left them out. Okay, so we start with this graph. And just one thing to point out is that there is an edge from E to Y and an edge from C to Y. So all three of these undirected edges, AE, AB, and AC, are technically these edges on possibly causal paths that I need to consider how they're oriented, right? So let's say that I start by considering A and E first in this argument. So I create two realities, so one where E points to A and one where A points to E. So in this case, where E points to A, I am able to, due to some acyclicity and conditional independence constraint, able to infer some more orientations. In this case, I'm not able to infer anything else. And so now I can ask, well, is the effect identifiable under these two models? So in this case, it is. So that's great. We get one effect from this graph. And let's look at this one. So this one still has these edges AB and AC undirected. So then we can orient AB in both ways and then still consider orienting AC in both ways. So in the end, this gives us, in this particular enumeration, 1, 2, 3, 4, 5 different kind of effects. This method would propose 5 different effects. However, it turns out these two ones in the middle here actually represent the same effect. And so what that means is that I can remove some of the information present in these graphs and I can still have identifiability. So what these graphs have in common is just this orientation AE and this orientation CA. The AB and BC edges are not in common, but it seems that they don't matter. So if I just replace these two graphs with this one, that just retains all the common information and kind of ignores the uncommon. This graph actually already satisfies the identifiability condition from that weird theorem at the beginning. And so why is that? Because something strange is happening here. It seems like this edge AB is still undirected, so how can this satisfy the criterion that there are no possibly causal paths that start with an undirected edge? So this graph in particular satisfies it because if you remember, we're dealing with directed acyclic graphs here. And if I allow this path ABCY to be causal in a DAG, well, then it's no longer a DAG, right? So you will never actually have a DAG where A is oriented to B and B to C, because that will create a cycle A, B, B, C, C, A. Right? So even though this path kind of looks like it's something to be concerned about, that it's possibly causal, in fact, it's not possibly causal. So if we, instead of doing this procedure, well, instead of doing this ordering of these orientations, so first AE, then AB, then AC, if we just did a different ordering, so we first considered AE, then we considered AC instead of AB, that ordering of the same procedure that we had on the previous slide actually gets you this graph immediately. So it immediately gets you to this minimal partition of 4 different total effects that are represented here. So our conclusion here was that this is ordering dependent, right? So it depends on what order you apply here, the operations in. And so we came up with slight modification of this idea, so that instead of just considering any edge, you just need to consider an edge that's on a shortest path. And the reason for that is that these shorter paths often determine the possibly causal status of the longer paths, right? So this edge CA that's on the path ACY determines the status of the path ABCY. All right, and we can probably show that this is complete and minimal according to our criteria, so that's really nice, and we have it implemented in R. And I think I should end here, but yes, I'm happy to chat about the other project as well. So the answer of these two papers says, yes, we can uniquely identify a set of possible total causal effects, but not how strong is this causal relationship. So that was another project, which I will skip, and I'll just go to the main end page here, which is to say that how strong is the causal relationship. We have some results on that we can use, so we can tell you how you can construct a nice efficient estimator if things are linear. If things are nonlinear, or if you don't want to assume that, things are more complicated. So we have some results on that, but they're not nearly as nice. And my big thing here is that this assumption, so of all the assumptions we made, what I think is the most restrictive one is this one where we assume we know all the variables. So this is not realistic in many scenarios. You just measure some. You cannot really assume that you measure everything. And there are many open problems if you go into the no part here. So we have some results on that, but this is not nearly as solved as this may appear. Yeah, many nice problems to work on there. Cool, thanks. That's all. Yeah. Sure.
Further questions for Emma?
I was wondering if, let's say, if I want to use some kind of causal model or learn a DAG
Mhm.
that represents
Yeah.
it. So I frequently work with experiments where I can sample everything and measure everything.
Oh, great.
But should I consider some kind of an experimental design so that I can eke out the causal information better than I would have than I would otherwise do?
Yeah, it's a great question. Okay, great. So I will try and repeat this. So you are in a setting where you can experiment and measure everything and get results of the experiments. And your question is, how do you match experimental design with something like this to make it more efficient or to do fewer experiments or things like that? Yeah. So there is actually a bunch of research on that, and it's like a super active topic currently. So from kind of the theoretical side, there are some results on, let's say, if you assume that you have the observational graph, like what are the minimal interventions you might want to do to learn the entirety of it. There's also some results on like optimization in terms of what are the batch sizes you would need, or like if you, given that you have this many samples. So I can direct you to those, happy to. I will say one thing that I find a little lacking in that area and is that all these results will assume that your end goal is to learn the entirety of the graph, which may not be your end goal. You may be satisfied with just knowing a part of it. That might be enough. Well, at least that's kind of what my research is about, I guess. And so there we're lacking a bit. But if you want to know the whole graph, there's like procedures you could use. Yeah. Yeah. Happy to chat. Yes.
So when you talk about this total effect, right, total causal effect,
Hmm.
are we having any probability distribution over each of those equivalent classes at the end to compute this? I mean, so you are kind of, go back to the previous slides where you have this enumeration over.
Oh, sorry. Yeah, I'm sorry. This one?
Yeah.
Okay.
So for each of this, there will be a separate causal effect, right?
Mm-hmm. Yeah.
So do you kind of also estimate an aggregate over all
Mm-hmm.
this?
Yeah, you essentially want to get like well, I'm assuming that you are interested in all estimates under the assumption that, let's say, that this one is the true model, that this one is a true model. You get like a point estimate in each case.
But at the end of the day, we want like a single estimate because that's what kind of, I mean, we want from the
Right. I don't think it really makes, well, I don't know, unless you are willing to commit to one of these models more than the other, I don't think it makes sense to rule out any other estimates. However, what you could do, and people have done this, is just take the minimum effect as like saying like the causal effect is at least this much. Of course, if this set includes a zero, then, you know, it's not great. But people have worked with the minimal effects to just say, I just want to bound it away from zero, essentially, in some way. Yeah, it's not a super precise answer, but yeah.
Can I ask one more
Sure,
question?
yeah.
So, I mean, this is not related to that, yes, but, I mean, how computationally, like, expensive is this?
Yeah.
If we,
Oh, great question. I have a slide about that, actually. Sorry, I have many slides extra. Yeah, there we go. because I get this asked a lot. Okay, let me walk you through this because it's a little complicated. So the global IDA here, or the global joint IDA, these are the methods that say I'm enumerating over the entire equivalence class. And this is exponential, so this is, you shouldn't do this. The fastest thing computationally is still to actually enumerate over the entire neighborhood of A. And the reason for that is that we can do that without kind of considering the rest of the graph. We can kind of just locally focus on it. If you want to do what we are proposing, which is to end up with this minimal partition, that is not as fast as what I just said. So that is not going to give, that algorithm is not going to be as fast. It's still going to be polynomial. Yeah, there's like an exponential term here, but this is because of the recursion. It's generally not a big issue unless you're dealing with infinite graphs, which we're not. So the main, I think, difficulty is getting the graph. So just to say that our approach is not something you should use if you're concerned about this. So the pitch of this project is actually, if you're interested in knowing that the estimates you're getting are causally different rather than just numerically different, then you should use our approach, but there's faster things to use if you just want a fast enumeration. Yeah. Cool.
That was inspirational, and I want to try the marshmallow test on my son.
Well, I should say that it was actually, it was debunked. And even actually Walter Mischel, in the end, in the last paper that's published on this and from 2020, which was published posthumously because unfortunately he passed away in 2018, admits that there is actually the effect is not as strong as originally publicized. Yeah.
What age did they start? How old were the kids with them?
They were, I think this says that the median age was 4 in 1972, so these people are now in their 50s. Yeah. Anyway. Yeah, cool. Thank you for your attention.